Okay, next we want to talk about supercritical fluid, finish up this section 5 and move into section 6 here of chapter 11. Okay, here's the example problem we just finished. Now, it turns out, just like we can heat up a sample to that phase change of boiling, there is another temperature at which we reach a supercritical fluid. Now, supercritical fluid is this interesting place where all of a sudden the barrier between gas and liquid, which you can kind of see as a line here, the top of the liquid, sort of goes away, and the material is no longer a gas and no longer a liquid. It's a supercritical fluid. Now, this usually doesn't happen under normal pressures, and so you're changing the pressure and you're changing the temperature. And so you're reaching this special phase we call a supercritical fluid. Okay? And the temperature at which we reach or become a supercritical fluid is just what's called the critical temperature. And this fluid now, remember, a gas is a fluid and a liquid is a fluid, so we're just talking about a fluid because it doesn't really have the properties of gas or of liquid, but it has the properties of both of those things. We don't know what to call it, so we call it supercritical because it's gone beyond this critical temperature. It's gone beyond this critical point where it has become this new fluid. Okay, so the temperature that produces a supercritical fluid is called the critical temperature, and the pressure at which you reach this supercritical fluid is also called the critical pressure. So you have the critical pressure and the critical temperature, and together those make the critical point. Okay, so the critical point is the point at which you reach the supercritical fluid. Kind of an interesting thing, really. And this brings us to the end of section 5 here. So we're on page 509 here, moving into section 6, where we're going to talk about sublimation. Now, I have an arrow here that describes, let's see, I got my animations a little messed up, but we're going to talk about moving between a gas and a solid and a gas. And the process of moving back and forth is the process of sublimation, or if you go the other way, of deposition. So that's what this arrow will show here. Let me go ahead and advance it so you can see. Got solid on one side, the gas on the other, and moving from the solid phase directly to the gas phase, skipping the liquid phase altogether, is called sublimation. And if you go the other way, from the gas phase directly to the solid phase, skipping the liquid phase, that's the process of deposition. Now, just like vaporization or evaporation and condensation, we were going from liquid to gas and gas to liquid. Here we're going from solid to gas and gas to solid. So we just give a new name to those phase changes. One is sublimation and the other is deposition. And this happens at particular temperatures and at certain pressures for different materials, right? So it turns out then a molecular solid can have a vapor pressure if it can go from a solid directly to a gas, which is kind of interesting. The sublimation process then would be like taking this solid chunk of ice and some gas molecules coming off of it. Now, this happens a lot for some substances that you know of, dry ice, for example. Solid CO2, carbon dioxide. Solid carbon dioxide, which we know is dry ice, is constantly like fuming. And it goes from being a solid chunk of what looks like ice to a gas directly, from CO2 solid to CO2 gas. It sublimates under our regular conditions when we pull it out of the freezer there. So it can undergo sublimation like that. Now, the interesting thing about it is this happens only for some substances and only in particular situations. And sublimation and deposition are the two phase changes. Now, we have other phase changes too, like you can go from solid to a liquid, that's the melting process. And you can go from a liquid to a solid, that's the freezing process. But when we think of freezing, we think of really cold temperatures, which is not always the case, right? You can go from a liquid to a solid at a higher temperature. Think of candle wax. It's at a high temperature and it cools back down, it solidifies, it's still at room temperature, even though it froze going from a liquid to a solid. It wasn't at a cold temperature, so instead of using the word freezing point, we're going to use the word fusion. So it fuses together to make a solid. So if it's going from a solid to a liquid, it's going to be melting. And if it goes from that liquid to the solid, it's going to be fusing or undergoing fusion. Okay? So as you heat a solid, its temperature rises, its molecules get more kinetic energy, they have more vibration, and they can overcome the attractions they have that kept them into their solid crystalline lattice and turn into the liquid phase. This is the melting point. And the temperature at which that happens, we know, is the melting temperature. And if you go the opposite way from the liquid phase and you cool it down, you remove kinetic energy, you remove heat, then what's going to happen is they're not going to be able to overcome the attractions they have for one another, those intermolecular forces, and they're going to freeze back into their solid form, or they're going to fuse back together. So it's the same process. It just depends on whether you're talking about from solid to liquid or liquid to solid. Okay, the opposite of melting is usually what we call freezing, but what we're going to know really as fusion here. So here's another heating curve, in this case of a solid, and we're talking about water. So we're going to start the water at minus 10 degrees Celsius. What do you know about water at minus 10 Celsius? It's a solid. Okay, so if you add heat, what's going to happen? It's going to change temperature up to some point, and then when it reaches that point, it's going to start changing phase. So we can calculate how much heat is needed to change its temperature up to 0, and then once it reaches 0, how much heat is needed to melt the whole block of ice, because all the heat you add is only going to go to melting the block of ice and not to changing the temperature of the solid anymore, or of what's become the liquid. Okay, that won't happen until the whole sample has melted away. So how much heat is needed to do that? Well, I'm going to need to know how much heat is required to melt a sample. So I'm going to look up delta H again. Remember, before was delta H of vaporization. Now I'm going to talk about delta H of fusion. Okay, it's just same as delta H of melting, but it sounds weird to say the enthalpy of melting. We're going to talk about the enthalpy of fusion. Okay, remember, same process, just going depending on the phase there. So what are the energetics of this melting process? How much energy does it take? And is it endothermic or is it exothermic? Okay, these high energy molecules, remember, in the liquid phase are going to lose energy to lower their kinetic energy value on average, and that means what they're going to do is freeze. And as they freeze, do they let out energy or do they absorb energy in? Okay, if melting is an endothermic process, remember, think of that block of ice. It starts to melt. When does it start to melt? When it's absorbed enough heat. So that melting process then requires an absorption of heat, right? Absorbing heat is an endothermic process. That makes your hand cold. Okay, so it's going to absorb heat when it's melting. It's endothermic when it's melting. Its delta H is positive when it's melting. And that means freezing then is the opposite. It's exothermic, okay? So in order to get something to fuse together, you have to remove energy from it. So it's an exothermic process. The delta H there is negative. All right, so melting requires an input of energy to overcome the attraction of the molecules, and freezing is the opposite. Okay, how much does it take to actually convert the sample from a solid to a liquid, or from a liquid to a solid? How much has to be put in or taken away? Well, it depends on each substance, and a certain amount of energy is required. We call that the heat of fusion, or delta H sub FUS. The heat of fusion, or the enthalpy of fusion, often is what we'll say. And that allows us to calculate the amount of heat needed to convert a sample between liquid to solid, or solid to liquid. Okay, melting or freezing or fusing, depending on how you like to say it. Remember, you're going to have to determine if it's liquid to solid or solid to liquid, whether it should be a positive value or a negative value. Okay, exothermic is negative, endothermic is positive. And you can see here plotted some of the different delta H of fusion values for these different substances. And it's important to note that delta H of fusion is generally much less than the delta H of vaporization. Okay? So that means the amount of heat to do this phase transition is much different than the amount needed to do this phase transition. Okay, it's just interesting on average. If we want to find the delta H, the amount of heat required for something to undergo sublimation, we're just going to add together these two delta H's, delta H of fusion and delta H of vaporization. When we add them, we will get the delta H of sublimation. Even though we're not going through the liquid phase, to do the transition is going to require the same amount of energy, and so we can find it by adding those two. Now, I don't think we really discussed that very much. So make sure you put a box around that if you ever have to deal with sublimation. Now here's that graph I was talking about, the delta H of fusion and vaporization compared. Notice for each of these samples, delta H of vaporization is much larger and much more significant, and a lot more energy is going to be required to vaporize a sample than just to melt it or fuse it back together. Alright, now let's do it over an entire process using each of these ideas together in one nice long problem. Okay, so if you'll look along with me here, actually, let's stop here because this is the end of section 6, and we'll start this problem at the beginning of section 7 in the next video. So I'll see you then.